on electric potential. All right, this will be the final chapter for test 1. So, all right, so all right, so we had electric field, which is given by the letter E, and we have electric potential, given by, more commonly known as voltage. All right. So, okay. So in a couple examples, we're going to deal with a parallel plate where we have plus, minus, and we're going to deal with charge. All right, now in here, as we had, the electric field goes across like so, and the electric field in two parallel plates, E is constant. All right, and depending on the charge, the units are volts per meter. So an example, say for this particular one, we have E based on the charge and the configuration. E is 1,000 volts per meter. All right. Voltage is V, the relationship V in volts, and V is E times D, where D is the distance that you're looking at here. So the separation of these two could be the voltage across here. All right, so if D, say, is 10 centimeters, which is 0.1 meters, and V would be 1,000 volts per meter times 0.1 would be 100 volts. So the voltage across this thing would be 100 volts. Or V we'll use. All right, so that's what we mean by voltage. All right. Now, all right, now if we put a charge in here, okay, this is a positive, positive charge here. So if we put a positive charge here and let it go, what's it going to do? Well, it's going to go flying across the other side, right? And we can figure out how fast it's going to go. What kind of energy is it going to have? It's going to gain energy. And the way it's going to work, remember back from last semester, potential energy is mgh, or mass. G is acceleration of gravity, and h is a height. So the potential energy is how high it is and how far it falls. Here, on the other hand, this has potential energy here, but the potential energy here is going to be given by the voltage times the charge on this particle. Okay. So if V, let's say Q is a proton, okay? And Q would be 1.6 times 10 to the minus 19th coulombs. Then the potential energy would be 100 times 1.6 times 10 to the minus 19th, or 1.6 times 10 to the minus 17th joules. So that's what we have there. Right. Right. Now, while we're dealing with, since we have electrons and protons are the main sources of movement, we have another unit here. We have the EV, which if you're in biology or chemistry, these are electron volt is a unit of energy dealing with on the atomic scale, like to energy to ionize an atom or get one from another state to another. We deal with this in EVs. We define one EV as the energy of one electron in 1 volt. And so we define this as 1 EV is 1.6 times 10 to the minus 19th joules. So in this case, if we have one proton electron 100 volts, this would end up being 100 EV. Right. So if you want to just express an energy, you use electron volts. But if you're actually trying to use MKS units, and we'll see that with the problem is how fast is an electron moving, then you end up with, this will be in joules. So that's what we call potential energy. It's exactly the same as MGH. It goes across, is given potential energy and going across there. So we're going to be dealing with this quite a bit. I'll only do one more example. And this is from the book. Okay. And, okay. So given the electric field and the separation between two plates, you can calculate the voltage. All right, so let's do another example. This is from the textbook. And we'll see, this is actually used quite a bit. In old TV sets, they actually have a plate, which is plus or a minus, and a little hole, and electrons are shot out, go through a hole, and would go onto the TV screen. And they'd be given a voltage, 5,000 volts, let's say. We'll also see this when we talk about X-ray machines, because X-rays are generated by accelerating electrons at very high speed and smashing them into a surface. All right, so what they'll have is this electron goes through 5,000 volts, going from repel the minus, go through the plus, and when it hits here, it'll have a certain speed. Now this is voltage, so I'll put down volts. V is that. I'm going to use little v. All right. This is the speed that it hits here. All right. So if this is an electron, then Q is 1.6 times 10 to the minus 19th coulombs. We're not going to deal with the minus sign here because we're only interested in the magnitude of this. So this would be the energy it would have would be 5,000 times 1.6 times 10 to the minus 19th. That'd be 8,000. That'd be 8 times 10 to the minus 16th joules. Okay. And then that would turn into kinetic energy of 1/2 mv squared. So it gains potential energy, much like a fallen object loses potential energy and gains kinetic energy. So we could calculate how fast this thing would actually be moving. All right. So the way we do this then is we would solve the mass of the electron is 9.1 times 10 to the minus 31st kilograms. So V, solving for V, would be, so multiply both sides by 2. Divided by m. And then take the square root of all that, because it's v squared. And we end up with 4.2 times 10 to the 7th meters per second, which is on the order of about 15% of the speed of light, c. So it's going rather fast. So that would be the velocity, the speed of this electron when it came out of this potential. So we're using the voltage, which is V, charge Q, that gives us a potential energy of, which is V times Q, and then that's 1/2 mv squared, where that's speed. And we solve for the speed. I'll put that again. This is little b, is that. So that's an example there of speed by a parallel plate, which is one way of accelerating electrons or protons sometimes. Okay. All right. Now we talk about moving on here a bit. Again, there isn't a whole lot to this chapter we're actually covering, so I'll leave that up for a second. Okay. And moving on here, and this room I have. All right, now we had from before, if we have plus, minus, the electric field goes like that for a dipole. Okay, now at points along here, much like we're talking about voltage, not voltage, but we're talking about height. For any, if this is a height, then anywhere the potential energy here is the same as the potential energy if we move it over any bit. Potential energy at both spots, 1 and 2, are equal because they're both the same height above the ground. So if we move it that way, these are what we call equal potential. We have the same thing with here, right? An electron, a proton, well, electron will go flying across to this side, flying across here. But anything like this, these are perpendicular. These are lines, what we call lines of equal potential. The book's got a pretty good picture of it. Lines of equal potential. And this is very similar to contour lines on a topographic map as shown in the text. So have you ever seen a topographic map and they have contour lines, say, of, going around a mountain of, say, 500 feet? Then anywhere along that line is the same height. So if you were to go hiking, you want to go in a circle without going high, you just follow the same contour line. So that's how that works there. These are lines of equal potential. Lines of equal potential. So anywhere here has the same potential energy to either move flying there or moving there. All right? Okay. Not much in here. Okay, anyway. All right. Now we're going to move on. So this is the dipole, the potential there. If we looked at a single charge, single proton, all right, electric field lines go straight out, as we talked about in chapter 16. Lines of equal potential, since it makes no difference where you are in here, would actually be little circles going around. So these would all be lines of equal potential. All right? And we would define, say, a particular one, if this is distance r from there, the voltage would be given by, where this is a charge at the center, would be given by KQ over R, where K is 9 times 10 to the 9th. I'm not going to get into the units, and this would be the voltage, volts, where Q is the charge in coulombs and R is in meters, coulombs, right? So that's the potential of a point charge. Okay. Right, and there's some examples there you can do. One thing about this is the potential of a point charge, V, and this is R, right? The potential will, as you get closer and closer and closer, it gets higher and higher and higher. So as you get closer, it starts to approach infinity. This is very similar to what we see for point charges of electron, if this is a proton, this would be basically a hydrogen atom. So what does the potential do with that? All right, classically, it gets worse and worse and worse. But we'll see at some point it actually changes as we get closer to a nucleus. And that's part of quantum physics and the way atoms work dealing with electrons. So how does it actually work? That's part of quantum theory. We'll get into that later in the semester. But for now, this is all I have to deal with, and that's the potential for a point charge goes as 1 over R. So that's section 17.5. All right. And then, all right, the last section we're going to do here, because we'll be using these later, is, like I said, a little bit on that. So The last section we're going to talk about is capacitance. And then we will be skipping the rest of the sections. So the last section we'll be covering is, I'll be doing 17.7 and 17.9. And the first one is capacitance. And basically what this is storage of charge. Now if you take an MCAT, they like talking about capacitance for the MCAT. Storage of charge. A battery is a capacitor, right? A battery is an example of a capacitor. You're storing charge in the battery, right? That can be used for something else, but that's what it's used for. And so a simple capacitor, and we'll get in this next, in more detail next, is we'll have charge plus, say Q plus, opposite charge Q minus on two plates. Separate the definition of that. And we use the unit C for capacitance. We use the letter C for capacitance, and the units are farads, capital F, right? So this is not coulombs. This is capacitance, capital C, and the units of farads named after Michael Faraday. So in a capacitor like this with charge Q and C, the relationship between Q, V, and the voltage, that separates these two would be C times V. So this would be in coulombs, right? So that's not capacitance. This would be in farads, and this would be in volts, V. All right, so you got it. It's very hard to keep track of all the units here. So this is C in coulombs, capacitance is farads, and V is in voltage. All right, so this is the only one that's consistent with that. All right. And we're not going to get into any details there. Last thing I want to get into then, since we're on this, is storage. We store energy in a capacitor or in a battery. The potential energy in joules is given by 1/2 Q times the voltage, so the charge on each plate or each side times the voltage equals to 1/2 CV squared equals 1/2 Q squared over C. Basically, using this relationship and substituting for each one. All right, so if we replace Q with CV, we end up with 1/2 CV squared. If we replace V with Q over C, we end up with that. All right, so this is a potential energy in a capacitor, and that's in joules. So that's how you store energy in a capacitor. And that is basically all of chapter 17. So this will be all we'll have for the next test as far as this is concerned. So we're doing about half the chapter. A lot of simple stuff. Read the handouts, read the PowerPoint, look at the work on the problems, and I will be doing a review